Welcome students. We want to talk about double integrals in polar coordinates. Before I start, I want to read this quote by George Boyle. Beauty in mathematics is seeing the truth without effort. So the goal of this lecture is now to compute double integrals in polar coordinates. So until now, whatever we did was in Cartesian coordinates, we had xy plane, but now we want to do double integral in polar coordinates. One of the reasons for doing so is the computation becomes simpler over region D when it is a special form, particularly special in terms of polar coordinates. So one of the special form of region over which you're integrating is essentially a polar rectangle. So what is a polar rectangle? So polar rectangle is a region in polar coordinates given by the inequalities x. So your r is between a and b. So recall r was the distance from the origin, right? So at any point your r is between a and b. So these are the values of your r in a and b, and your angle theta is between alpha to beta. Yeah. Also recall the relation between the Cartesian polar coordinate was x equals to r cosine of theta, y equals to r sine of theta. So if you're given r and theta, you can go to xy using this. And if you're given xy to r theta, the connection is r equals to square root of x square plus y square, and theta equals to tan inverse of y over x. So this is so what is a polar rectangle? So polar rectangle is where r is changing between fixed values a and b, and theta is changing between fixed values alpha and beta. So recall we had integral. So our integral was roughly of form f of x psi star y star uh, delta x delta y, which actually can be written as dA. So the differential area, and these were double summations, and then you are taking the limits. So suppose I going from 1 to m and j going from 1 to n, limit m and n both going to infinities. So this is how you define the region. You define the double integral of f of x y o dA. So we want to do the similar story here. We would like to replace f with, instead of x, we'll have x is, so if you're in this region here, so the premise is you start with a polar rectangle of this form. This is your polar rectangle. Then you divide it into, you do the subdivisions of this into smaller polar rectangles like that. So we get something of this form here. And then what we do is the following. We have, so in this rectangle, suppose you have r changes from, so in this rectangle we have r is between ri minus 1 to ri. So that is your r is between ri minus 1 to ri, and your theta is between theta j minus 1 to theta j. So you get this rectangle. So the way you think about your function is, instead of x, so I have f of xy dA over region R, I can replace it by, x can get replaced by, so if you want to write it as Riemann sum, let's write it as Riemann sum. So this will be, so I will replace x by Ri cosine theta j and star, and I'll replace y by Ri star sine theta j star summations. Now the summation is over different I and j. So let's use I and j going from, so k, j going from 1 to L. It depends on how many subdivisions you did of your rectangular, polar rectangular region. And then you have still have dA. Now you want to write this in terms of r and theta. Yeah, that is our goal. And then if you let limit k and L go to infinity, you will get your coordinate. So we are transforming now in this case, writing everything in terms of polar coordinates. So now we have figured out what x and y should be replaced with, but what about our differential area? So look at the differential area. In this case, in our case, it looks like a polar wedge, right? So this is your A, and we want to compute what is this dA. So dA equals to, what is our question mark? So recall, what is the area of a sector? So if you take a circle of radius r, so suppose you have a circle of radius r, and this angle is suppose theta, then what is this whole area? So the area of this sector is given by, so it is going to be, the total area is, so area of this sector. So the total area of the circle is, if the radius is r, it's going to be pi r square. However, theta, so you're not taking the whole area, but you're taking the piece or slice of that area of ratio what? Theta over 2 pi. So this is what the area of this sector is going to be. And what is the area of this sector? So this can be written as half r square theta, right? So pi and pi will cancel. So we'll be left with, this is equal to half r square theta. So this is the area of the whole sector. So now this can help us to compute the differential. So notice the following, we can think about this as half. So this whole thing is, so this part is r until here. So this is our r. This is d theta. This is dr. Let's call this as delta r for a moment. So what is our delta A? Delta A is going to be this total area of the sector, the whole thing, which is going to be, so in this case we have half, the radius is r plus dr or delta r, so r plus delta r, the whole square. The angle is fixed, which is delta theta, minus half, and this part is going to be, now we are going to look for the inside part, which is this from here to here. So we are going to remove this region now. This region is what we are going to remove, right? So from there we remove this, we get half r square delta theta, and simplification will take us half delta r, so we can write it as delta r square minus delta r square, sorry, minus r square delta theta, and this can be replaced by now half is going to be a minus b times a plus b. So a minus b is going to be delta r, and a plus b is going to be plus this plus this divided by delta theta. So this can be now 1 delta r delta theta, and we can have 2r plus delta r, and we can ignore this term comparatively, so we get 2r by r. This is going to be roughly r delta theta. So in this way we can write an approximation. So dA is going to be r dr d theta. Okay, so if we replace that back here in the previous example, we get this gets replaced by r dr d theta. Okay, and that's how we get an integral in for over polar rectangle. So let's just rephrase this. So over a polar rectangle, so suppose f is a continuous function on a polar rectangle R, where R is given between A and B, as in the previous example here, and R is between A and B, and theta is between alpha. So this is alpha to beta, alpha to beta. This angle is beta. Then we get integral r f of x y dA is going to be, so x gets replaced by r cos theta, y gets replaced by r sine theta, dA gets replaced by r dr d theta. Okay, so this is how you convert from Cartesian to polar coordinates. Let's look at an example. Things will get clearer in this case. So suppose evaluate the region R, where region R is given by 3x squared plus 4y squared dA, where R is a region in the upper half plane bounded by circle x squared plus y squared equals to 1 and x squared plus y squared equals to 4. Let's first draw the region. So if you draw the region R, this is our region R, and if we look at it, it basically, so in this case we have, so the first circle is x squared plus y squared equals to 1, implies r equals to 1. And then for the second one, we have x squared plus y squared equals to 4, implies r equals to 4. R square equals to 4, my bad, x squared plus, because the equation of a circle is given by x squared plus y squared equals to r square. And we get, so 1 square, r square equals to 1. So in this case, we get r square equals to 4 and r equals to 2. So in this case, our region D is going to be r theta, where our theta is between 0. So the angle is 0 here to pi. So theta is between 0 and pi, and r is between 1 and 2. So this is what our region is. So therefore, this integral can be written as r 3 plus 4 y square dA can be written as integral. So I'll use theta for, I'll choose to do r first. So 1 to 2, 0 to pi. I have to replace everything x with r cosine theta, and then y will be 4 r square sine square theta, and then instead of dA we have r dr d theta. Yeah, so this is your dA, and dA gets replaced by that. All right. So now let's integrate this. So first I'll integrate with respect to r. So I get this is equal to, so this integral is going to be 0 to pi. Now 3 r square, integration of 3r square is what? R cube cosine theta plus 4r cube. Now 4r cube is basically integration of 4r cube is r to the power 4 sine square theta. So we have integrated already with respect to r. R goes from 1 to 2 of then d theta. So we get in this case it's going to be, just to make distinction clear, I'll write r equals to 1 to 2, and so we get 0 to pi r square. So r cube, so 2 cube is 8, 8 minus 1 cube, so 9, so 8 minus 1, so 7 cos theta plus 16 times 16 minus 1, so I have 16 minus 1 sine square theta d theta. And then this can be integrated in the following way. Again, 0 to pi 7 cos theta plus 15 by 2. I'm going to convert this using double angle identity. So note that sine square theta is 1 minus cos 2 theta divided by 2. So this is going to be 1 minus, so this is going to be 1 minus cos 2 theta, which is divided by 2, which went here, d theta. So now then the whole answer is going to be 7. Integration of cos theta is sine theta 0 to pi plus 15 by 2 theta minus sine 2 theta divided by 2 again 0 to pi. So what will survive in all this thing is, so sine pi is 0. Similarly, cos pi is also, sine pi 2 times pi is also 0. So what will essentially survive is 15 by 2 pi. So the answer turns out to be 15 by 2 pi. Now, note that the success we had in general region, so recall, we started this story with integral of double integral over rectangles, and then we went on to general region, x first and y first region. So same thing we can do for polar coordinates as well. So we have what is called as general R first region. So this region is described by the following. So your region D over which you're integrating is R theta, where R is between fixed alpha and beta, whereas, sorry, your your R is between h1 theta and h2 theta, whereas your theta ranges between alpha and beta. If this happens for your region D, then it is given by double integral r f of xy dA. Again, x is replaced by r cos theta, y is replaced by r sine theta, dA is replaced by r dr d theta. Now, since you're doing with respect to r first, so r changes from h1 theta to h2 theta. So this is what we get here. And then we have your theta changes from alpha to beta as we have here. So d theta alpha to beta. So this is how a general description in our first region looks like. And if you look at the diagrammatic view of it, this is your region. So your r, which is a distance from origin, when you hit the arrow in direction of r, along the r, it hits first the curve h1 theta, and then it comes all the way out to r equals to h2 theta. And then your angles are between alpha to beta. So in that case, this is a description of our first region. We can have a similar description for theta first region as well. But let's first work on the following problem. So region, find the area of region R bounded above by y equals to x and below by the circle x squared plus y squared minus 2y equals to 0. So let's draw this region first. Before we go further, let's understand the circle properly. So x squared plus y squared minus 2y. We want to write it in the standard form. So we'll add middle term divided by 2, which is 1. So 1 on both sides. So this gives me x squared plus y minus 1 square equals to 1. So it's a circle whose radius is shifted up to, instead of 0, 0, it's 0, 1, and the radius is still 1. So let's draw this. So this is how your region looks like. So this is a circle of radius 1, but the center is 0, 1. And this is a region whose area you are interested in. So you're interested in this area of this guy, right? So how would we go about it? Let's describe this as our first region. So, so we need to write this down, this equation down in terms of polar coordinates. So we have, if you look at this equation, x square plus y square minus 2y equals to 0. If you let x equals to r cos theta, y equals to r sine theta, this will transform into r square minus 2r sine theta equals to 0. So here we get r equals to 0 or r equals to 2 sine theta. And this is the equation of this circle. So we have r is 2 sine theta. And where's your angle changing from? Your angle is changing from 0 all the way till pi. So let me write this region D down. So region D is r theta, where my r is between 0 to 2 sine theta, and my theta is between 0 and 2 pi. So I need to find out region, area of the region. Note that how do we do area of region D in terms of Cartesian coordinate? It's just simply integrating function 1 dA over r. Now we'll write this in polar coordinates. So essentially we are integrating r dr d theta. This is the r first region. So our r is changing from 0 to 2 sine theta, and theta is changing from 0 to pi. So this computation will give us the area. So let's compute this. So this is going to be r squared by 2 for r. R goes from 0 to r equals to sine 2 theta, and then 0 to pi of d theta. And this integral is going to be half outside, half 0 to pi 2 sine square theta. So it's going to be 4 sine square theta d theta. Now that can be written as 1. So 2 can go out. 1, 2 will be consumed to write down 2 sine square theta as 1 minus cos 2 theta d theta. So again, that is going to be, this will cancel out. We'll be left with theta minus sine 2 theta by 2, 0 to pi. Well, if you substitute in the second part, you will get 0. So the only answer turns out to be pi. So this is your region, area of this circle. And it kind of makes sense, right? Because after all, this is a circle of radius 1, right? Okay. However, note the following. Instead of solving the other problem, I managed to solve a wrong problem here. I solved basically this problem here, right? So I found out area enclosed by, so I found out region R enclosed by the circle, right? Now let me remodify this problem to include our earlier constraints. So now I have to modify my problem because I ended up reading problem in a different way and ended up solving a different problem. Nevertheless, in this case, we are looking for the following region. We are looking for region bounded above by line y equals to x. So this is our region y equals to x, y equals to x, and below by the circle. So we are interested in this region here. So how do we find that? So we need to again find what is our D. So D, so in this case, this is our R, right? So R again is the distance from origin, so it's still changing along the circle. So we have R is between 0 and 2 sine theta. However, what about theta? So what is this angle here? So y equals to x. So this line has angle 45 degrees or pi by 4, right? Let's just see. So what do we get? We get r sine theta equals to r cos theta gives me tan theta equals to 1, which means theta equals to pi by 4. So this becomes, so we are looking at r theta, where theta is between 0 and pi by 4. So this angle here is pi by 4. So pi by 4. So let's compute this. So again, the integral will look like double integral over region D. If this region is D, the area of D is going to be 1 dA over this region D, and that is going to be integral 0 to 2 sine theta. So R, so instead of D, I'm going to write R dr d theta. R changes from 0 to 2 sine theta, and angle changes from 0 to pi by 4. So we get, this is going to be again r squared by 2. This is the integral r squared by 2, 0 to sine 2 theta, sorry, sine theta. And then whatever you get, you integrate with respect to theta. So now we get, this is r squared by 2. So this is 0 to pi by 4. This is going to be 4 sine square theta by 2. So it's going to be 2 sine square theta d theta. However, this can be now solved using double angle identity. So this is going to be 0 to pi by 4, 1 minus cos 2 theta d theta. And that can be seen as theta minus sine 2 theta by 2, 0 to pi by 4. So when you put pi by 4, we get pi by 4 minus, so when you put pi by 2, so pi by 4 here, so you get sine pi by 2, which is 1, minus 1 by 2. And when we put 0, we get 0 in both. So this is the area. Right, so early on I solved a different problem. Now this is a different problem. All right, so now we found out the region R, area of region D or R. Yeah, so since it's R, let's call this R because this is saying it R. Okay, so this is R, region R. Okay, now let's look on to the next problem. Find the volume of the solid that lies under the paraboloid. So z square equals to x square plus y square, which is this paraboloid here. And in the above the xy plane, and inside the cylinder, x square plus y square equals to 2x. So this is your cylinder. So essentially we're looking for this area here. It's a 3D solid figure, and we are looking for what is the volume of this region, volume of this solid, which is inside the cylinder, but what under the paraboloid. So below the paraboloid goes like that, and we are interested, even in that case, we are just interested in this part here. So let's find out how will we. So again, the first step is to look at the footprint of this in the XY plane. So the footprint of this in XY plane is again going to be a circle. So let's look at that. So let me get the cylinder first properly. So this can be written as x square minus 2x plus y square equals to 0. And if you add 1 on both sides, you can see x minus 1 square plus y square equals to 1. So this is essentially the footprint will look like in the xy plane will be of the following form. So when I draw this, this is how the footprint will look like. Essentially, this is your y-axis, this is your x-axis. And this point is going to be 1 comma 0. Now we need to write down the polar equation of this circle. So it's going to be, if you look at this equation again, we get x square is plus y square is r square. So I'm going to replace quickly these two guys with r square. So r square minus 2r cosine theta equals to 0. Just take r common. So we have r minus 2 cos theta equals to 0. So r equals to 2 cos theta, r equals to 0. So what is my region D going to be? So region D in this case is going to be r theta, where r is between 0 and 2 cos theta. And well, what about my angle? My angle goes from, in this case, if we see the angle, it's from here, which is minus pi by 2 to pi by 2. So theta is between minus pi by 2 to pi by 2. So now what is my, this is my function, right? So I need to integrate f because I'm integrating what is below z, which is x square plus y square, and inside the cylinder, right? So we get, in this case, we get we get basically the following. So integral of over region D of x of xy dA is going to be, this is my z. So I get r square. So z is equal to, so in this case you have z equals to r square, right? Because it's x square plus y square. And instead of dA, use a different color. dA is r dr d theta. This is my dA. And what is happening with r? R is between 0 and 2 cos theta, and whereas angle is from minus pi by 2 to pi by 2. Now let's work it out. So we get, this is going to be r cube. So integration of r cube is r to the 4. So we have minus pi by 2, 2 pi by 2 r cube, which is r to the 4 divided by 4. R goes from 0 to r equals to 2 cos theta d theta. Now this becomes, this is same as, so 2 cos theta is, so power 4 is going to be minus pi by 2 to pi by 2 r to the power 4. So 2 to the power 4, which is 16 by 4 cos to the power 4 theta d theta. Now we want to be able to integrate this. Now note that what kind of function is this? This is a even function. So when you have minus a to a and you're integrating even function, it becomes 2 times that. So the net is going to be 2 times 8 times 0 to pi by 2 cos of 4 theta d theta. Now we would like to integrate this. So for that we have double angle formulas. So this will be, sorry, this is going to be 16 by 2, which is 4 times 2 is 8, not, so it's going to be 8 times this guy. So now we need to use double angle formula. So what does double angle formula tells me? It tells me that I can double the angle. So this is going to be 8 times 0 to pi by 2. What is cos square theta is 1 plus cos 2 theta divided by 2 the whole square d theta. Now this 4 can go out, so we have 8 by 4, which is 2, 0 to pi by 2. Now expand inside, so 1 plus 2 cos 2 theta plus cos square theta d theta. Right, and now again we need to convert this into double angle. So we have 2, 0 to pi by 2. Now it's all mechanical, one-dimensional integration, right? So we have 1 plus 2 cos 2 theta plus cos 1 plus, so cos 4 theta plus 1 divided by 2. That is what your cos square 2 theta is, d theta. Now let's integrate this. So we have 2 times theta plus 2 sine 4 theta, sorry, my bad, 2 sine 2 theta divided by 2 sine 2 theta divided by 2 plus 1 by 2 sine 4 theta divided by 4 plus theta, bracket close, 0 to pi by 2. Now if you put pi by 2, this will become pi, this will become 2 pi, so they will become 0. So what is left out is 2 outside, theta plus theta, so we have theta plus half theta, which is 3 by 2 theta, so we have 3 by 2, theta is pi by 2, and then rest, when you put 0, this will become 0, this will become 0, everything becomes 0. So we have this angle, which is going to be 1 to 1 to cancel, so 3 pi by 2. So this is what your area is, sorry, volume is inside the cylinder and below the paraboloid. All right. Now consider the following problem. So consider the double integral 0 to square root of pi by 2 minus pi square root of pi minus y square sine square plus sine square dx. So first of all, we need to sketch and describe the region. So here, if you look at x is changing from y to x equals to square root of pi minus y square makes it look like x square equals to pi minus y square. Yeah, so it's a circle of radius pi, right? Sorry, square root of pi, right? This implies x square plus y square is square root of pi, the whole square. So I will draw this region. So I need a circle of radius. So let me draw the x-axis. This is my y-axis. This is my x-axis. So first, I'm having x first. So x first moves in this direction. It hits y equals to x or x equals to y. Line x equals to y is, you can draw a rough sketch. I'm just trying to draw as accurate as possible. So I get, this is a line I'm interested in. So this is y equals to x. And then it hits out to this part of the circle. This is a region for x. Now, what about y? Now, y changes from here to, let's see. So y is from 0 to square root of pi by 2. So 0 to square root of pi by 2. So let's see, what are those intersections? So we have, if x equals to y in this equation, if x equals to y, we have what? X squared plus y squared equals to pi. So if they are equal, we get x squared plus 2x squared, sorry, x squared plus x squared, which is 2x squared, equals to pi, which means x equals to square root of pi by 2. So this is indeed the point, all right? This is the point where you have what? X equals to pi by 2. So this angle is pi by 4. Why? Because y equals to x always leads to pi by 4. Why is that? Because let's see. So y equals to x implies r sine theta equals to r cosine theta. This gives me tan theta equals to 1. So theta equals to pi by 4. Particularly, we are interested in the first quadrant, right? So this is a region. And I want to write down now this region in terms of, so this is region. So region D in polar can be described as R is changing from, so it's r theta, where r is changing from 0 to square root of pi, and my theta is changing from 0 to pi square root of, so theta is changing from 0 to pi by 4. So this is the region. Now we need to integrate over this for this function here. So let's write down the polar coordinate of this region. So this region is going to be, this integral is going to be r. So since it's a rectangle, now we can do either way, either one first. So I'll go for 0 to square root of pi. Theta goes from 0 to pi by 4. Sine of r squared, r dr d theta. So this is the integral we want to compute. So here we can use substitution, right? So integration of sine is minus cosine. So this integral can be shown to be minus cos of r square divided by 2. So I'm basically multiplying and dividing by 2 so that you can do the substitution properly. And the limits are 0 to square root of pi. And this limit is for r, right? If you want to make sure that there's no mixing happening, you can do like this, 0 to pi by 4 d theta. So this is going to be 0 to pi by 4 of, well, now what is cos of? So this is going to be minus cos of pi minus cos of minus plus cos of 0 divided by 2 d theta. Note that you can also do the breaking it off as two integrals because r and theta are independent. However, uh, we could have done that too. So we get minus sine. So this is 1 plus 1 divided by 2. So it's going to be 1. So 0 to pi by 4 of d theta, which is going to be pi over 4. Let's solve the problem. All right. So now we are conversant with how to compute the polar coordinate integral in polar coordinates. Now note that this integral, if you wanted to do it directly, would have been extremely ugly if you did not do it in polar coordinates. Yeah. So for example, if you try to solve for y would have been square root of 1 minus plus or minus 1 minus 1 minus x minus 1 the whole square. That is already going to be ugly. So it was a good idea to convert that into polar coordinates. Now let's look at the following application. So suppose you're integrating minus infinity to infinity e of x squared dx. So how do we go about it? First of all, before I solve this integral, I want to point out that this integral is very important integral in statistics. For example, a probability density function with mean mu and standard deviation sigma is given by this, where what kind of distribution you have for a normal distribution. Yeah, for a normal distribution. Yeah, so for normal distribution, this is a probability density function. So you can see already integrating this density function is important for us, and this is the integral we get. So let's prove this. So we wanted to show that this is square root of pi. So let's start with I square, which is going to be integrating this e to the power minus x square dx integral of minus y square dy, right? So this is going to be integral minus infinity to infinity, minus infinity to infinity, e to the power minus x square plus y square dx dy. Now we are basically going to convert this into polar coordinates, namely the following. What we'll do is we'll make it a circle. So we will have, if you convert this, you can think about, so this is actually essentially integral over R2. So if I write this integral, this is essentially integral over R2 of e to the power minus x square plus y square dA. Now there are many interpretation of R2. One interpretation could be that you are having a disk of radius A. So dA is disk of radius A. So you can compute this integral as integral over disk of radius A e to the power minus x square plus y square dA, and you let limit as a go to infinity. All right, so if you do that, that would work out. So now in this case we have x square plus y square is r square. So your dA can be thought of as the following region. So before I write it down, so dA is a region r theta, where theta goes from 0 to 2 pi, but your r is between 0 and a. So this integral then transforms. So I square goes to limit as a goes to infinity e to the power minus x square plus y square is r square, so minus r square times r dr d theta 0 to a, theta is 0 to 2 pi. Now I just want to show you that you can also break the integral in this case. So this is going to be 0 to 2 pi of d theta, 0 to a of e to the power r square r dr, limit as a goes to infinity. So you can break it like that. So we get this is equal to 2 pi. Now this is going to be e to the power r square by r square, the whole divided by 2, 0 to a, limit as a goes to infinity. And that, if we compute, is going to be pi. So I squared is pi, implies I is going to be square root of pi. And that does our job. Okay, so now we want to consider find the region R bounded by the cardioid R equals to 1 plus cos theta. So if you recall, this is how the cardioid looks like. So we have R equals to 1 plus cos theta. So we want to basically find out. So this is our region D. We want to find out the area that is similar to integrating, 1, right? So 1. Now I would directly do the integration. So first of all, let's write D. So what is our D going to be? So D is going to be, so your R is between, so it's R theta, where your R is between 0 and 1 plus cos theta, and your theta is between 0 and 2 pi. So we have 1 dA, that is what our region is, and this is our integral, but let's write this integral now in polar coordinates. We have r dr d theta. Here r is going from 0 to 1 plus cos theta, and your theta is going from 0 to 2 pi. So this is our area, and this is going to be 0 to 2 pi r square by 2. So you get put 1 plus cos theta, the whole square, divided by 2 d theta. And this can be shown as 3 pi by 2. Okay, so this is an example you should work yourself. So note that this is an intersection of a cone, z equals to x squared plus y squared, below the sphere and above the cone. So when you draw the sphere, so this is how a sphere will look like. So this is a scenario. So first you will need to project it down to this circle here. Okay, and this will be your region D. Okay. All right, so good luck. Thank you for your time.